Hi, my name is Chad Kwong, and I'm here today to talk to you about an interesting algorithm that isn't quite commonly used now, but could have great applications in the future. I am talking about the Metropolis Hastings algorithm. Before we can get into the grand scheme of the Metropolis Hastings algorithm, however, I think it would be a good idea to review some key concepts covered within the algorithm itself. Our first topic to review is Markov chains. In order to fully understand what drives the Metropolis Hastings algorithm, we need to have a firm grasp on the concept of Markov chains. Markov chains are models that analyze the state of an observation and the likelihood of changing to a different state or triggering a different event. These types of models deal with graphically structured data. In terms of graph data definitions, we can think of the nodes of the data as our states, and the edges between nodes as the transition probability between each state. The last thing to keep in mind about Markov chains is that they are stochastic models that abide by the Markov property. Without getting into the complexity of the property itself, the outcome of the Markov chain models satisfying the Markov property is that predictions of the current state can be made independently of the past and/or future states of the system. This ultimately means that predictions can be made on the transition of a system solely based on the present state of the system, and that it is not necessary to account for the past or future states of the system. A good use case of a Markov chain that would demonstrate this trait of memorylessness would be Google's PageRank model. In this model, websites can be thought of as the nodes, and hyperlinks that connect each website can be thought of as the edges between nodes. The model ultimately assigns a value to each page based off of the number of backlinks associated to that website, where a backlink can be thought of as a one-way link from one website to another. Memorylessness tied to the Markov property would be demonstrated in this model through the aspect that if you are on one website, the only probable connections to your current state are the websites that are directly connected to the one that you are currently on. The transition to one website or from one website to another does not depend on the websites that have no direct connections to the one that you're currently on. This trait of memorylessness allows Markov chains to pragmatically deal with randomness. Moving on from Markov chains, our next topic to review can be considered as one layer deeper than Markov chains. I am of course talking about Markov chain Monte Carlo methods, or MCMC for short. The MCMC method involves producing samples from an initial system that simulate some target distribution using transitional probabilities extracted from the system's Markov chains, hence the name Markov chain Monte Carlo. I say that the MCMC method simulates a target distribution because in the MCMC methods, random samples are pulled from some uniform prior distribution and are then evaluated to determine if they fit some likelihood distribution that is proportional to the posterior distribution that we are trying to achieve. While it is very possible to have a likelihood distribution that is the exact same as the posterior distribution you are trying to represent, most MCMC methods achieve a representation that is at the very least proportional to your target. Additionally, these likelihood distributions are created from random samples by evaluating them through the use of transitional probabilities from the prior distribution to the posterior distribution. This process for an individual sample can be considered as a random walk. Because MCMC methods are used to simulate a target distribution by sending random samples on these random walks, they are excellent candidates for at least two use cases. The first is when you want to sample from some population that proves to be difficult to sample from. In this example, MC-MC methods could therefore be used to stage data for the analysis of specific, hard-to-reach populations within the data provided. The second use case is when you want to solve more complex integrals. Mathematically speaking, the visual representation of an integral is the area underneath a curve defined by some function. This should sound extremely familiar, as a distribution can be seen as the area underneath some probabilistic curve. Through the transitive property of mathematics, we can then say that the mathematical approximation of some integral is equal to the area underneath a distribution curve that matches the function within the integral. Moving on from MC-MC methods, it is now time for us to talk about the main topic of my presentation, the Metropolis-Hastings algorithm. So what is it? Well, the Metropolis-Hastings algorithm is an MC-MC method used to simulate a distribution. The algorithm produces a sequence of random samples that fit a target distribution density by using Bayesian inference to determine the validity of each random walk performed by the model. And so in this process, the Bayesian inference is ultimately an acceptance criteria posed by the algorithm, and so for each random walk, a random sample is evaluated and then is either accepted or denied based off of this acceptance criteria. So the results of a Metropolis-Hastings model are samples of data that match a distribution density that is proportional to the target posterior distribution. So in this graph on the right, we can see that the blue dotted line represents our prior distribution from which we are pulling samples from, and the green line represents the posterior, which we are trying to reproduce. And now this graph labels the red line as a posterior as well, but it specifies that it comes from the MC-MC method. Well, this posterior is ultimately the likelihood distribution that I had been referring to earlier. So it is the prediction that our algorithm is ultimately making to assume that that based off of the density function matching the posterior, that this posterior or this likelihood function that is being predicted should match the posterior in some way. So moving on, I want to talk about just a few assumptions of the algorithm itself. The first assumption of the Metropolis-Hastings algorithm is that there is some stationary distribution pi of x, such that pi of x is equal to the desired posterior distribution. And this distribution pi of x must exist for the system being analyzed. To expand on this, a distribution can be considered stationary if it is unaltered by any operations performed on it or unaffected by other matrices. A second assumption that isn't quite necessary but is definitely preferred is that there is a detailed balance within the stationary distribution. Detailed balance requires that each transition within pi of x is reversible from x to x prime and vice versa. This can be compared directly to Bayes' theorem, which states that the probability of A given B multiplied by the probability of B occurring is equal to the probability of B given A multiplied by the probability of A occurring. And our final assumption of the algorithm is that the stationary distribution that we have defined must be unique. This uniqueness in the distribution is ensured through a Markov chain feature called ergodicity. A Markov process can be considered ergodic if all the states in the system are aperiodic. This ultimately means that pulling samples from the population will represent the original system fully and allow one to deduce all statistics of the original population from the system. With the assumptions outlined, I would now like to move to another important aspect of the Metropolis-Hastings algorithm, the acceptance criteria and its definition. And so I had briefly mentioned this acceptance criteria in the previous slides. And so this acceptance criteria is how we evaluate each random sample on the random walks performed by the MC-MC method. This acceptance criteria can change from model to model. However, I will be deriving the most common one. So to begin the derivation, let us first start with the condition of detailed balance, as I talked about on the last slide. You'll notice that this is just simply a rearrangement of Bayes' theorem, substituting x prime for b and x for a. So, moving on, we can rearrange this equation as two ratios that are equivalent. So we have the ratio of predicting the outcome of transitioning between states, and we set that equal to the ratio of the probability of occurrences for each of these states as well. And so we'll have the probability of x prime over x is equal to the probability of x prime given x over the probability of x given x prime. Now, let's suppose that the probability of being in state x prime given state x is equal to some proposal distribution g multiplied by some acceptance distribution a. The proposal distribution can be seen as the probability of hypothesizing the state x prime given x, and the acceptance distribution can be seen as the probability of accepting the hypothesized state x prime. And so if we substitute this back into our original equation, our original rearrange equation, I should say, we get the following. Rearrange this equation to get a ratio of acceptance, ultimately a ratio of the acceptance distributions. And this is ultimately equal to the probability of x prime occurring times the proposal distribution from of x given x prime over the probability of x occurring times the proposal distribution of x prime given x. And then we choose an acceptance ratio that matches the conditions described above. Now, the most common, and why I previously had inferred that this could be more open-ended, is that the most common choice for the acceptance ratio is the Metropolis choice. Well, hence the name Metropolis Hastings model. And so by applying this Metropolis choice, we arrive at the following equation, where the acceptance distribution for x prime given x is equal to a minimum function. So we cap this function out at 1, but it ultimately equals the ratio of the probability of occurring for x prime over x times the proposal distributions of x given x prime over x prime given x. And ultimately where the proposal distribution is equal to 1. So with our acceptance probability defined, we can then construct the actual algorithm. The algorithm can be broken up into two essential steps, initializing and iterating. As a part of the initialization, we pick an initial state x naught, and we set t equal to 0 for this initial state. We then begin the iteration process, where we generate a random state x prime according to our proposal distribution of x prime given x of our current state, and calculate the acceptance probability, or the acceptance distribution as I had called it earlier, a of x prime given x. And then we accept the random state that we initially proposed, so we accept our x naught at t0, and we generate a uniform random number, we accept or reject the random state, so that if the random number within the state is less than the acceptance criteria, less than or equal to, I should say, then we accept the state x prime that had been proposed, and then we set x sub t plus 1, so the next iteration, equal to our proposed state x prime. And of course, if we have to reject the proposed state x prime, then we reject it and simply set x sub t plus 1, so the next chronologically iterative state, equal to, well, our current state. So essentially what that means is that we're restarting that iteration, but providing a different random sample to evaluate. And then ultimately, at the end of each iteration, we of course set t equal to t plus 1, and then we iterate, or we repeat, and we keep on iterating until the model produces a distribution that we seem fit. So moving on, the most common application of the Metropolis-Hastings algorithm is to solve complex integrals. Take the integral on the screen, for example. If we were to set d pi of x to d of x and h of x to 2x, then we would have a simple integral of 2x dx, which is of course equal to x squared over the space of chi as supposed in the equation. However, what if we want to solve a much more complex equation to integrate over? For example, I've taken in-depth physics classes. I majored in astrophysics in my undergrad, and definitely getting into quantum and some statistical representations of heat systems themselves. So you get some very complex equations that ultimately proved to be impossible to solve by hand. So this is a prime candidate of a use case for the Metropolis-Hastings algorithm, because we can essentially evaluate what those integrals equal by using the information that we do know about the system and creating a density function that'll represent our system. And then by performing these random walks, we can approximate what the ultimate value that we're trying to achieve ultimately is. And so, with this in mind, solving complex integrals, the most main use case for the Metropolis-Hastings algorithm as of now is really just used in computational fields of study. And these can range from physics, like I had said, to biology, to chemistry, and even consider statistics as well. I think I saw one paper about using a Metropolis-Hastings algorithm to, produce a sample population I can't remember exactly, but it was having to do with natural language processing and staging the data to analyze a particular population. So there's definitely some lesser known applications of the Metropolis-Hastings algorithm, but it's still it's such a widely applicable algorithm, in my opinion, because it ultimately can be used in any situation using Bayesian statistics and ultimately Markov chains in general. And then, like I said, even if the primary use, like I said, would be when it's just hard to sample from a population in general. So with these use cases in mind, I would like to propose some potential future applications of the algorithm as well. So given my background in physics, one of the things that I like to talk about commonly and study on my side time is quantum computing a little bit. I wouldn't say I'm a subject matter expert, but I definitely find a lot of fun in just reading about the news and catching up on the physics from time to time. But the power behind quantum computing is the ability to perform parallel calculations through the superposition of states in what are known as qubits. And qubits can be seen as the quantum equivalent as bits of information, where bits, lie on the scale of 0 to 1. Through quantum mechanics, qubits still lie on the scale of 0 to 1, but it is not expletive. So, through superposition, it can either be 0 or it can be 1 at the same time. It is at the state in between. So, with this in mind, quantum computing allows a vast architecture of parallel computations to take place within one system, because each bit can be assigned to calculate a process. Furthermore, the direct result of this parallel computing architecture is the ability to go through incredible amounts of data with great efficiency, which is why quantum computing poses as such a huge threat to modern security and technology. However, one drawback to quantum computing today is that on a smaller scale inputs and data, the processing speeds are much slower than traditional transistor-based computers for most applications. Well, so I pose this question. Can we use the Metropolis Hastings algorithm to somehow improve the performance of quantum computing by isolating the distribution of states between qubits? If this is the case, then we could then use this to isolate the states of the qubits to simulate transitional two-state bit systems of transistor-based computers in order to bridge that gap between traditional and quantum computing. A second smaller potential future application that I sort of thought of off the top of my head is, I think there could be, a real justification in using this to for law enforcement investigative analytics. So pose the question of trying to profile a suspect, or just even trying to represent a population of defect people. Well, I shouldn't say it like that, but people who are not fully representative of the full population. And if we want to study these in terms of crime analytics, then we would need some way to form a population that can be analyzed. And while I'm sure there are handfuls of actual criminals out there. It would also help to take the people that we do know are criminals based off of our justice system and produce samples based off of that distribution as well. So that's just one possible application that I also thought of. And then additionally, this is the last one that I kind of thought of. Was applying it to construct a model to verify our own history. And so with this, it seems like today, there's definitely a common perception that, for some reason that, observations in science isn't completely reliable. And, to some extent, I guess I can see how some people think that. And I think that also applies to history as well. And this one is a little bit more absolute in the fact that we know that history is always written by the victors. But if history is always written by the victor, how can we truly know that the victor's interpretation is arguably sound to what factually occurred? By setting a target distribution of the population we have today, we can perform a series of walks using this method to verify that historical events we have recorded to produce the outcome population that we have today. This is just an idea, though, and it's not been investigated further, and I'll admit it could make absolutely no sense at all, but, I like to think of weird ideas sometimes and just throw them out there and see what sticks. So furthermore on this, I should say this would also require us to, probably find proof of ergodicity in our, history, which essentially means that our history shouldn't be aperiodic, or it should be aperiodic, I should say. And, well, we definitely know that history seems to repeat itself in more cases than none. So these are just a couple potential future applications, just because the research that I had put into this algorithm didn't really turn out with a whole lot of use cases, and I found that to be quite boring, if I'm being frank. So I just decided to throw a little creativity into the mix. So moving on to the general conclusion. The Metropolis Hastings model is an MC-MC model used to produce samples within a desired distribution. The method is mostly used for computational fields of study that are more focused on producing observable results than the interpretation of the model that produces the results observed. And while one main application is computational physics, we must also remember that physics equations representing systems are more widely applicable than you can think. However, this isn't a physics presentation, so I won't, spoil anything like that. So with that being ado, thank you very much, and good night. Bye-bye.